Okay, so we looked at the example where we had to find the maximum area of a rectangle placed under a parabola. We looked at the maximum area of a trapezium that was under a straight line. We did it on the video by dividing a trapezium into a rectangle and a triangle, and on the memo there was an area of the trapezium used, so you could compare the methods. Now, what about this example? It almost looks as if we have too little information given, because they are asking us to determine the maximum area of a rectangle that is drawn inside an isosceles triangle for which the height is double the length of its base. Now, what's the first thing missing? Well, for me, the first thing missing is the graph, because the first two examples that we looked at both had Cartesian plane. Now here we don't even have a triangle that is given to us. So let's start there. Let's bring our triangle and try to draw a rectangle inside it. Okay, so we have our triangle. Let's call this triangle ABC. It's an isosceles triangle, which means that the perpendicular height will bisect the base. And what we know is that if I look at the base AB, then I know that the height, let's call this height OC, is going to be double the base. Right, so the first thing is we at least now have a triangle. Now, what's happening in this triangle? Well, inside this triangle, I would like to place a rectangle. So let's call this DEFG. Okay, I've got this rectangle, and I want to maximize the area of this rectangle. So it starts looking a little bit like the two other examples from the previous video. What's the last thing missing? Okay, the last thing that it's missing is actually a Cartesian plane, because I could solve the last two examples only because I was looking for the area under a curve, which then requires a Cartesian plane. So let's be clever, and we're going to extend the base and create the x-axis here, extend the height and create the y-axis in there. So now I'm going to give some dimensions to my rectangle. So I'm going to say that the side OB has a length A, so the same, therefore AO will also have a length A, which means that the height of this triangle is 4A. How this helps us? Well, this point then, as a point on the Cartesian plane, has coordinates that I know the values of. X coordinate is 0, y coordinate is 4A. A point B, as a point on a Cartesian plane, has an x coordinate A and y coordinate 0, which means that I can now determine the equation of this line, and I could look at maximizing the area of this part of a rectangle, which then looks a little bit similar to our trapezium problem. Pause it, think about it. The only way to solve the area of a rectangle drawn inside the shape is if we have a Cartesian plane and we know the equation of the graph that we are inscribing the shape under. So can I find the equation of a straight line CB? Okay, CB will be y equals to mx plus c, which is our 4a, where the gradient is our change in y over change in x. So we've got minus 4a over a, okay, rise over run, which is minus 4. Okay, so our equation of this straight line is minus 4x plus 4a. Remember, a is just represents the constant, the dimensions for my triangle. Why do I need it? Well, you remember that the point that lies on a curve with coordinates x and y is the point that can move along, that therefore it determines the size of our area. Now I can look for the area of half of my rectangle, which is then OD times DE. OD is x, DE is y, but the y coordinate of the point E is the same as my equation of a straight line. So that area is x times minus 4x plus 4a. So I get that my area is minus 4x squared plus 4ax. I found the area of half of my rectangle. What will be the full area of the rectangle? Well, obviously, we just need to multiply this by 2 because it's a perfectly symmetrical shape. How to maximize that area? Well, in order to maximize the area, we need to find the derivative. So let's carry on with our calculations. Okay, so if the area was twice minus 4x squared plus 4ax, then a will be minus 8x squared plus 8ax. Okay, will it be possible for us to determine a minimum or maximum? Well, obviously, this area will only have a maximum, since it's a parabola with arms down. And in order to determine the maximum value, we need to find the derivative of a given function with respect to the given variable. So we get minus 16x plus 8a. Derivative must be equal to 0. Therefore, we get 16x equal to 8a, and x will be equal to a over 2. Okay, so if a to my rectangle will have a maximum area if I choose x as a over 2. Remember, the base was twice a for my isosceles triangle, but I will maximize the area if x is a over 2. The question was to actually determine the numerical value of that maximum area. So therefore, the maximum area will be if I substitute my x as a over 2 into the equation. So I get 8a over 2. Okay, so we get minus 8a squared over 4 plus 8a squared over 2. So we simplify and we get that the maximum area is minus 2a squared plus 4a squared. So the max area is 2a squared. Okay, where you remember we were analyzing an isosceles triangle with the base 2a and the height 4a. That will then be a maximum area of a rectangle inscribed inside the isosceles triangle. Pause it. This is not given on the worksheet. This is definitely a double star question for everybody who would like just a bit more challenge in terms of area under the curve. Please do now the summary worksheet and check with a memo, turn in, and good luck.